In this series of videos, we are going to be looking at how do we graph a rational function. So we got some steps here for us to go over, and then we have a bunch of problems for us to practice with. So the first step is to make sure that we completely factor our function and identify the domain. Now, we've done this in previous videos. Find what the domain is, start there so you know what values of x are useful and which ones are not. Then you want to make sure that you write your function in lowest terms. Now this means, if there are factors that reduce, you need to reduce that. And we mentioned previously how if you do have a factor that reduces in the numerator and denominator, that can create a whole. So we have to make sure that we incorporate that correctly into the graph. The next part here is if 0 is in the domain, then you have this for your y-intercept, right? Every y-intercept is going to be 0, whatever. And as long as 0 is in the domain, you would just take the a sub 0 and b sub 0 to that quotient, and that's going to give you the y-coordinate for the y-intercept. And for x-intercepts, you're going to set the numerator equal to 0. Okay. Now, for this next part, we identify all the vertical asymptotes by setting the denominator equal to 0. So we've got to make sure we keep those guys straight. So vertical asymptotes will come from setting the denominator equal to 0 once we have our function in lowest terms. The x-intercepts come from setting the numerator equal to 0. In other words, you're trying to figure out what makes the numerator equal to 0, because 0 over whatever, as long as it's not 0, is going to give you 0, which will then lead to your x-intercept. And step 5 is to identify any horizontal or oblique asymptotes that you have and check for intersection points, because it is possible that your graph will intersect your horizontal or oblique asymptote. Now, it doesn't do that all the time. Sometimes it does, sometimes it doesn't, but we do need to check for that. Once we have all that key information down, we want to make sure that we use that to form our graph, and those asymptotes really help us figure out the shape where our graph is going to be located, especially once we throw in x-intercepts, y-intercepts, and then if we use a t-table to find additional points. Now, when I say make a t-table, that means pick values of x that are close to where all the action is happening. So, for example, if you have a vertical asymptote at x equals 3, it might be worth your time to check what the function gives you at x equals 4 and what x equals 2. You don't want to say, oh, let me plug in 10. If 10 is nowhere near where all the action is, then don't include that. Look at the stuff that's going to be around, say, the origin, around where you have your vertical asymptotes. Okay, so let's start with this example right here. Okay, r of x is equal to x squared plus 1 over x minus 1. Seems simple enough. Now the first step is to completely factor this. And there's not really much to do. X squared plus 1 does not factor, so we leave it just as it is. But we want to identify the domain. So remember, the domain will be all real numbers unless it's a value that makes the denominator equal 0. So we can see from down here, if we were to let this equal 0, that means x equals 1 is going to be that restricted value. So for step 1, my domain is going to be all real numbers except for 1. Okay. Step number 2 is to write our function in lowest terms. Well, since x squared plus 1 doesn't factor, this guy is in lowest terms. So this part is done. All right. Is 0 part of our domain? Well, yeah, 0 is going to be in this little part right here. So we can identify the y-intercept as being 0, something. And what you want to do is that you want to look at, well, if you plug in 0, all you have left would be the plus 1 over negative 1. So we would have the y-intercept at 0, negative 1. We want to check for x-intercepts. So for x-intercepts, maybe you go up here to the side, you say, okay, I need to set this numerator equal to 0. But if I do that, I find out that, let's see, x squared is equal to negative 1, which means x is equal to plus or minus I. So there are no real solutions to this. So that means for your x-intercepts, we We don't have any. So it's not going to cross the x-axis whatsoever. Okay, so we've got the domain, we've got the y-intercept. Step 4 is to find the vertical asymptotes by setting the denominator equal to 0. So that's in the reduced form, which is what we have. So step 4, my vertical asymptote, is going to be x equals 1. That seems to make sense. That's where we have the issue with our domain. Now, in a previous video, we talked about how we identify horizontal and oblique asymptotes. So if we look at this, we can see that the degree of the numerator is greater than that of the denominator by exactly 1. And if we were to focus just on these pieces right here, the leading guys, x squared over x reduces to x. So that means as x gets really, really big for this function, it's going to behave very closely to x, or something of that sort. Maybe like +1, +2, something like that, but it is going to be focusing on x. So see if we can figure out what that is. So we know that there is no horizontal asymptote, but we're going to do the division to find the oblique asymptote. Now again, I like to use synthetic division if I can. So since I'm dividing by x minus 1, my k value is 1. In my coefficients, I have 1x squared, 0x, and 1 for the constant. So we bring down the 1, and we do the whole back and forth thing. Multiplication with the k value to get 1. We add here to get 1. Multiply to get 1. And we add to get a remainder of 2. So translating this means that we have an oblique asymptote of y equals, check this out, this is going to be 1x and then plus 1. Okay, so that kind of gives us a bit of a framework to work around as we go out to the ends for our end behavior. So step 6 is to take the key information that we have and just start to put it in the graph and see what we can come up with. All right, so let me scroll back up here a little bit. So we have our domain. The y-intercept is 0, -1. So that's going to be right there. A vertical asymptote of x equals 1. So vertical here at x equals 1. And we have our oblique asymptote at y equals x plus 1. So that would be starting right there and having a slope of 1. Okay, let's make sure we do this nicely and neatly, coming back the other way. So right now, that means that our graph is going to be fitting within these, in the divisions that we have with our asymptote. Now, here is something that I think is interesting. This point of intersection that we have right here at 1, 2, this intersection with our asymptotes, oftentimes, but not always, can act as a point of symmetry. So for rotational symmetry, I mean. So if I look at this point that I have right here, if you count it, this guy's down 1, 2, 3, and 1 to the left. So down 3, 1 to the left. If I reverse that and go from this intersection point up 1, 2, 3, and then to the right 1, I should have another point. Now, we can verify this if we do what we say here in step number 6 and just create a t-table of values just to get a better idea of what we have here for points. So it looks like I plotted the point 2, 5. Let's see that. If I plug in 2, what was my expression? X squared plus 1 over x minus 1. So x squared plus 1 over x minus 1. If I plug in 2, that gives me 2 squared plus 1 is 5 over 2 minus 1, which is 1. And we get 5, which is exactly this point that we have right there. Well, I might want to plug in 3 just to get an idea of what's going on as I move out to the right. If I plug in 3, 3 squared plus 1 is 10. 3 minus 1 is 2, and I get 5. So I can mark that point right there. Now, as I was talking to you about this point symmetry, See how this point is 1 to the right, 3 up, and you have a partner that's 1 to the left and 3 down. Well, what about this guy, this new one? It's 2 to the right and 3 up. If I go 2 to the left and 3 down, I should have the corresponding point right there. Now, looking at where these points are and knowing how my shapes typically go for rational functions, I think it's pretty safe to assume that my function is going to be curving in this part up here and then in this bottom left part down there. So let's just do a quick little sketch. So it's going to turn, and then here's the thing about your oblique asymptote. As I get further and further to the right, he's going to get closer and closer and closer to that. Where if you go up far enough, that rational function compared to the oblique asymptote, those guys are going to be practically indistinguishable. All right, so we're going to finish this guy off down here. Make sure that you're graphing to the edge of the graphic window and put your arrows at the ends. So something just like that. Now let's take a moment and let's check this with our graphing calculator. All right. So big parentheses, we have x squared plus 1 divided by x minus 1. All right, let's graph. Oh, look at that. Look up. There we go. That is just what I have, right? And we can even come back over here and let's graph what we said our oblique asymptote was, which is x plus 1. And we can see how nicely that matches up with our original function as we go out towards the boundary marks, right? And we can even check the table if we want to get some extra points. So we were checking at 2. Oh, I'm looking at the wrong. Okay, yeah. So we plug in 2, we got 5. Plug in 3, you get 5. If I were to plug in 4, I get 5 and 2/3. So at 4, you'd be at 5 and about 2/3 right there. So yeah, everything that we see here is definitely matching up with the graph. So figure out what you know piece by piece, right? You find the little things. You find the domain, find the asymptotes, find the intercepts, and then you find extra points to kind of fill in the gaps with our knowledge. And then before you know it, it's going to be done.